We are given a non-negative integer, x, and need to find its square root without using any built-in math functions. If x is exactly 4, the answer is simply 2, since 2 times 2 is 4. But what if x is 8? 2 squared is 4, and 3 squared is 9. Since 9 is too large, we have to round down to the nearest valid integer. The correct answer remains 2. The goal is to identify the largest possible integer whose square remains less than or equal to our target number. We can visualize this by laying out all possible answers from 1 up to x on a continuous number line, with their corresponding squares written right below them. Notice how the bottom row behaves. As we move from left to right, the square of each integer gets progressively larger. This sequence is naturally sorted. Because the search space is mathematically sorted, we don't have to check every single number one by one. We can skip that slow approach entirely and use a highly efficient binary search. To set this up, we need 3 standard pointers, f on the left, ls on the right, and mid in the center. We also need an empty variable called res to hold the best candidate we find along the way. Whenever the middle pointer lands on a number whose square is less than or equal to x, that number is a valid candidate. We store it in the res box to keep it safe before we continue searching to the right for an even larger valid number. Here is a diagram showing the integer limit trap. If we test our condition by multiplying mid times mid, testing a large number like 50,000 will quickly exceed the maximum integer limit and cause an overflow error. We fix this by dividing x by mid instead of multiplying mid by itself. The resulting number stays small and fits safely within the system limits. Using division ensures our boundary checks are mathematically accurate, allowing the algorithm to run without crashing. Let's run the algorithm with x equal to 8. Our left pointer starts at 1, our right pointer starts at 8, and our midpoint evaluates to 4. We test 4 against 8 divided by 4. Since 4 is not less than or equal to 2, this candidate is invalid. The right pointer shifts to 3, and the entire upper half of the search space is eliminated completely. Look at the remaining search space. Where does the next middle pointer land, and what happens to our empty res box? The new midpoint is 2. 2 is less than or equal to 8 divided by 2. This is a valid match, so the number 2 is saved into our best candidate box, and the left pointer moves up to search for anything higher. As the loop finishes its final iterations, it continuously updates the stored candidate. When the pointers cross, that box holds the absolute highest valid floor value. Here is the code next to our search space. The while loop represents halving the number line. If the division passes, we store the midpoint as our candidate and shift the left boundary up. Otherwise, the else statement forces the right boundary left, discarding upper numbers. The code is a literal translation of the physical boundary shifts and candidate storing mechanics we built on the number line. By cutting the remaining options in half with every step, the algorithm slices through massive amounts of data in logarithmic time, giving us an O of log x time complexity.
First, I'm going to check the base cases. If x is equal to 0 or 1, I will simply return x because the square root of 0 is 0 and the square root of 1 is 1. After handling the base cases, I will initialize 2 variables, first with a value of 1 and last with the value of x. I will also initialize another variable named result with 0, which will store the current best answer. Next, I will implement a while loop that continues as long as first is less than or equal to last. Inside the loop, I will calculate the middle value using the formula mid equals first plus last minus first, y2. This is the preferred way to calculate the middle index in binary search because it prevents integer overflow. Then, instead of calculating mid times mid, which can also cause overflow for large values, I will compare mid with x squared mid. If mid is equal to x squared mid, it means I have found the exact square root, so I will return mid. If mid is less than x mid, it means mid squared is less than x, so mid is a valid answer. I will store mid in the result variable and continue searching on the right half by updating first equals mid plus 1. Otherwise, mid squared is greater than x, so I will search on the left half by updating last equals mid minus 1. Once the loop finishes, it means an exact square root was not found. In that case, the result variable contains the largest integer whose square is less than or equal to x, so I will return result.